important task of this particular phase. And as I mentioned again and again, that it uses the syntax directed translation scheme to perform that. So in order to generate 3 address code from a given for a given programming language, we basically use some predefined functions and attributes, which I'll be explaining to you as we go forward. In your exam, it is quite possible that you will be given a program and you have to translate it into corresponding intermediate code using all the notations you have seen in your class. So please remember these things, because in exam you might not have to explain all these things, but you are expected to remember all these things. So we have the temporary names. I have already talked about temporary names. The function new temp returns a sequence of distinct temporary names. So each time you call new temp, it returns T1, T2, T3 in that sequence. That means it creates a new temporary and returns it to the ICG. Similarly, there is a predefined function new label, which returns a sequence of distinct labels, L1, L2, like this. So this is these are some of the assumptions we have of the ICG. Now, the synthesized attribute s.code represents the code. I'll shortly explain what is meant by code. And then, what is S? S is basically sentence. Okay. And E is nothing but the expressions. So you can have arithmetic expressions as well as logical expressions. They are all represented as E as a convention, and S for sentences or statements in your program. So s.code is the attribute for S. For E, we have two attributes, e.place and e.code. We'll see that for logical expressions, we have something else also. And you can readily understand it would be e.true and e.false. So all these things are there. Now, the very first thing we are going to discuss is the declaration type of statements in your program. So what does the declaration part do? As you know, it creates symbol entry for each declared name. In the symbol table, the name is included, the type is included, and the location in memory, that is the offset, is also stored. Okay. That offset can be from a standard location, like from the top of the activation record in case of procedure calls. For local data, that's how it is. It can be different for other parts of the data, like global data. So here you can see the production rules corresponding to declaration. So P produces D. So you can think of P as the declaration, starting of the declaration section. And then you have a bunch of declarations which are delimited by semicolon, which is D producing D semicolon D. Each of the declaration is of the form ID colon T. That means you can have a sequence of declarations where you have the variable name, then a colon, and the type name. So
this is a part of L attribute.
Yeah. Actually, it doesn't really matter here, because we are mostly concerned with synthesized attributes, as I said. So yeah, these are S attributed as well as L attributed, both. Because most of the time we are focusing on Bison-like parser generator, and we are not really working on top-down parser. So in a bottom-up parser, it's mainly synthesized attributes. For some attributes which are not synthesized, we'll show you how to get the values. We have seen those issues in SDT, and we are going to use the same solutions. So you can have something like this as your declaration section. So it could be, say, ID1 colon integer semicolon ID2 colon real, like this. So this is basically the declaration section. So you can think of declaration section is populating the symbol table. You can think of this way. So it is the symbol table, and there are a few divisions here. This is basically the name part. This is the type, and this is the offset. Offset means where should it be placed in memory. As you know, this is very important as far as runtime memory is concerned. So here, the first entry is going to be ID1. Its type is int, and its offset is 0. I assume that. The second one will be ID2. Its type would be real, and its offset would be, say, 0 plus 4, maybe 4, like this. ID3, similarly, will be starting from 12 because we assume reals are.
And how we are calculating the offset part?
I'll show you. Okay. So my point is, this is what we want. So whenever we have a declaration section, we want the symbol table to be populated correspondingly. So these are three attributes: name, type, and offset. Oh, I'm sorry. So this is how you declare the variables, and this is how you enter the identifiers or variables in the symbol table. As you can see, there is a name field, there is a type field, and there is an offset field. Now the question is, how are these things done in the semantic actions? As you can see, whenever you have a production rule deproducing ID colon T, it calls an inbuilt function enter. The function enter does nothing but populates the symbol table. So what are the parameters it expects? It expects the name parameter, which is nothing but the name of the identifier. It expects the type. Type, as I said, could be integer or real, and then the offset. Now, how does it know what is the type? As I said, type can be integer or real in our example. So it populates the t.type attribute as integer or real, as the cases may be. And then if it is an integer, the width is populated as 4. For real, it is populated as 8, reflecting 4 bytes and 8 bytes respectively. So that means what? That means when you are calculating the offset of a particular identifier to be entered in the symbol table, you need to keep track of the offset variable, and that offset is set to 0, as you can see. Whenever the ICG encounters the declaration section first. In that case, the offset is initialized to 0, and then whenever an integer or real is encountered, that width should be actually added to the offset. And as you can see, whenever we have deproducing ID colon T type of statement, which is the actual declaration statement, then first you use the existing offset and then you increase the offset by the width of the identifier. So in case of an integer, it would be 4. In case of real, it would be 8. So this is how I have populated the value here. Is that okay, Pranay? Can you see this? So ID1 is entered at the offset 0. ID2, which
Yes,
occurs after ID1, which is an integer, will start at offset 4. and ID3, which is something, but it occurs after the identifier ID2, which is a real, so it should start from 12. Okay, this is how the offsets are calculated. There are two more constructs here. Unfortunately, I don't have the time to explore these things. One is the array, and another is the pointer. I'm thinking of giving you an assignment. Maybe there you will be exploring these things a little bit. This would be a theory assignment, and those who have not appeared in the exam physically, I might consider this submission for some credit. Okay, but I'm not promising anything because nothing has come from the management side. So, but I'll still give you the assignment, which will consist of a few questions, and you have to write some answers and submit it online so that I can evaluate. I promise that I'll be adding some credit from them.
Sir, it will be theoretical or some
Theoretical.
numerical?
It will be only theoretical. Theoretical means all problems, theory problems.
Yes, sir.
Okay, so that was the declaration statement part. Next comes the another easy part, which is the assignment statements. Okay, as you can see, the production rules are on the left hand side. So you can have E producing E1 plus E2 or E1 star E2. These are basically the arithmetic assignments, arithmetic statements. E producing minus E1, E producing within parentheses E1, or E producing ID. And of course, in order to complete the assignment, you need to have ID colon equal to E. So you evaluate the expressions, and then those evaluated expressions are assigned to another ID identifier. That is the significance of having assignment statements, which are nothing but arithmetic assignment statements. Okay, now let us see what this is doing. So let's just take one example, which is E equal to E1. E produces E1 plus E2. So you have something like this. Say A is assigned the value B plus C. Okay. So in this particular case, we have E producing E plus E, and this is producing B, and this is producing C. Okay. And then we have S and ID, then colon equal to, and then this. Okay, this is basically the parse tree. So what is E plus C doing? So what is your expectation? Your expectation should be something like this, that in your intermediate code you will have T1 equal to A plus B. So A plus B will be assigned to a temporary. That is the first task. And you are not wrong. You can see the corresponding semantic actions here. E dot place is new temp. As I said here, there are two attributes, E dot place and E dot code. E dot place is the name that holds the value of E. It is generally a temporary, and E dot code is a sequence of three address statements which is attached to E. So here, E dot place is new temp. That means E should be held into a new temporary. So in our case, it starts from T1. So we have T1, which is the corresponding E dot place for E. So this is where it is E dot place. And it should be a new temp, so it should be T1 here. And then E dot code is equal to E1 dot code followed by E2 dot code, and then you have the corresponding inbuilt function gen, which is E dot place is assigned the value E1 dot place plus E2 dot place. So it's nothing but new temp T1 is assigned the value A plus B. Okay, so this is a semantic action. Now, what happens if you have something like this? A plus B minus C. B plus C minus D. In that case, as you can readily understand, so you will not have these. So what will you have? You will have something like this. So this would be E producing E plus E. This is producing B. This is producing C. And then this is producing D. So now what would be the semantic action? So for this part, you will have T1 is assigned the value A plus B. Okay. For this part, the whole thing, now we have this left E is placed in T1, the right E is placed in D. So we need a new temporary T2, which will hold the value right here. So this will be T1 minus D. Okay. And then the whole thing is assigned to S like this. So what would be the semantic action for S producing ID colon E? It is S dot code is nothing but code for E followed by ID dot place is assigned the value E dot place. So here ID dot place is A, and where is this E stored? Right here. This E, it is stored in T2. So we can say A is assigned the value T2. So you see how the tree address code is created for arithmetic expressions. Okay, so here we have to just be careful about two things. One is E producing E operation E, or E producing E1 operation E2, whatever way you think about it. So you have to create a new temp and you have to append the code for E1 and E2 and then generate a statement which will create an assignment statement, temporary assignment statement in tree address form for E dot place, E1 dot place, and E2 dot place. Note that before you know E dot place, you already know the values of E1 dot place and E2 dot place. So you can easily synthesize this statement. And then the other statement is S, which is ID colon E colon equal to E. That means the assignment statement in our programming language, which is nothing but the code for E followed by a statement ID dot place is assigned the value E dot place. Okay. Now, as you can see, Gen actually appends the code instead of generating the code actually. So, in order to speed up the process, this is a better translation mechanism where you don't have to keep on building E dot code really a large string. You don't have to do that. Instead of that, you use the call emit. So emit exactly does what gen does, but instead of appending the code, it immediately spits out the code into the terminal so that your intermediate code is generated as you go, translating the expressions and assignment statements one by one. So it is an incremental translation. Instead of keeping all the code and then at the end uh, generating the output. So this is the more convenience feature. So instead of gen and carrying the E dot code, here the only thing is that everywhere you encounter the E producing E1 of E2, of course you have to calculate the E dot place, which is nothing but a new temp call. but then you use the inbuilt function emit, which does what gen does, but instead of appending the code, it just outputs the code into the terminal. For id assigned the value e, as you can see, there is a lookup call which makes sure that id is actually entered in the symbol table. So here, um, if you are using a for the first time, you have to make sure that somewhere here you have a colon the int. This is there, so that a is actually entered in the symbol table before this assignment statement is encountered, and that is a requirement for some languages as well. Similarly, you can see the code for e producing id, where also the lookup function is used, which will make sure that the identifier is actually entered in the symbol table and there is a pointer to that available before you try to assign e dot place into this, or this value into e dot place. So e dot place should be assigned the value p by looking up, but it makes sure that it is not null. If it is null, that means if the identifier is not entered in the symbol table, that means we run into an error. That means it is a undefined variable error, which we encounter very often when we do the C programs. So this is not really suitable for more advanced languages where we declare on the fly, or sometimes there is no declaration needed at all. Implicit declaration is good enough. But this language is slightly less capable than that. Okay. So arithmetic expressions and arithmetic statements are gone. Now we will be going to the second one, which is Boolean expressions or logical expressions. So they compute logical values, but the problem with Boolean expressions is that unlike arithmetic expressions, they are not always standalone assignment statements. They are always, in general, they are always used as flow of control statements. So a smaller than b, d smaller than e, a greater than or equal to e, these kind of comparisons, which are Boolean expressions, are generally used with flow of control statements like if then else or while do, like this. So we need a little bit more sophisticated method of translating the Boolean expressions. Note that we are not really going into the flow of control right now, but we'll see that even with Boolean expression translation, we have a flavor of flow of control. So these two actually, flow of control statements and Boolean expression translations, go hand in hand and just complementary to each other. Now the first method is you can have a numerical way of translation where you assume that true is represented as 1 and false is represented as 0. This is one type of compiler. In the other one, which is a flow of control type of translation, here you basically don't assume anything about true or false, but since logical expression in general evaluate to true and false, you can just assign positions. So you can say a smaller than b will take me to e dot true or e dot false depending on the evaluation of the logical expression. And you will see that it is very often not necessary to evaluate an entire expression, because if you have a or b or e or b, sorry, e or e producing e1 or e2, if e1 is true, that means e is true also. And similarly for and, where if e1 is false, then e is also false. So you don't really need to evaluate e2 at all. Now, let us do the translation here. Very similar to what we have done here. Is here we have something like a smaller than b. So the translation scheme is like this. If a smaller than b, go to some place and there you I'm sorry. Yeah. So it's like A or B. So what you can do here is you can do a similar translation. Q1 is assigned the value A or B. Okay. So that will tell you whether T1 is true or false. I mean, depending on the value of T1. So if A or B evaluates to 0, that means T1 is false, and A or B evaluates to 1 means that means T1 will be true. So this is how you assign numerical values. Okay. Um, so if you have something like this, like the example here, A or B and not C, then it will produce this kind of three address sequence. T1 is assigned the value not C. Then, because not has the highest precedence, it is a unary operator. You know, unary operators are always having the highest priority. That is how the grammars are. Then you do B and T1 and assign it to another temporary T2, and then you assign A or T2 to T3. So this is a perfectly okay way of translating logical expressions, but you can understand the biggest problem is whether uh, the you actually want to follow the convention of T1 being 0 as false and T1 being 1 as true, that kind of scenario. But assuming this is the scenario, then you can see what it does. So E1 or E2, just what we did for E1 plus E2 in arithmetic case, we create a new temp and assign E dot place to that, and then we emit E dot place is assigned the value U1 dot place or E2 dot place. Similarly for and not. But that's not all, because as we know, Boolean expressions can have relational operators. So A or B is not good enough. You can have A smaller than B, that kind of expression. So what to do with that? This is slightly complicated, and this is where logical expressions tends to get more challenging. So suppose I have this kind of a scenario, A smaller than B. This is a logical expression. So this is something like this, E producing a relational operator and another relational operator. This is something like this. So what should be the translation scheme for this? So the rule is E producing ID1 relation of ID2. So what should be the translation scheme? Now, this will be something like this. If A smaller than B, go to somewhere and then you assign a temporary the value 1. Actually, we'll do this way. Suppose this is statement number 100. Okay. So if A is smaller than B, if it is true, you might want to go somewhere. And where do you want to go? Naturally, you should have this statement in between. You are trying to evaluate a smaller than b, either 1 or 0. So how can you do that? You can say if a is smaller than b, then go to such a statement so that the temporary you are intending to populate gets the value 1 or 0, as the case may be. And there should be another statement which will direct to the false part, and there you will have one is assigned a value 0. This is how we want the translation scheme. So instead of evaluating a smaller than b as 1 or 0, we let a corresponding statement take that action. So now what you can do, if a is smaller than b, you can say go to 101, and then you can say go to 103. As you can see, this doesn't make too much logic. So instead of that, why don't you do this? Go to 103. So if a is smaller than b, go to 103 and assign the value 1 to t1. If it is not true, let it fall through to 101 and assign t1 to 0. And then you ask this guy to go somewhere else, which will be later than 103. That way you can complete it. Okay, maybe we'll make it as 104, assuming this is the statement which follows a smaller than b. As you can see, if a is smaller than b, it will come to 103 and then fall to 104. If a smaller than b is not true, it will come to 101, assign 0 to t1, then go to 104, skipping t1 is assigned the value 1 statement. So this is how we like relational operator based expressions to be translated. So this is how you see E producing ID1 relational operator ID2. So you assign E dot place a new temporary. Then we emit if ID1 dot place relational op ID2 dot place go to next at plus 3. Why next at plus 3? Because the following statement would be assigning 0 to E dot place, and then that will be skipping over 103 or next at plus 3 using the go to statement. Here the next stat is nothing but the next statement number. So for example, in this example, when you are at 100, the next stat is 100, and you have to add 3 to get to 103, where you can assign 1 to t1. Similarly, when you are at 102, you can say next stat plus 2 to skip over the truth assignment statement. This is how you can translate the relational operators, and then your expression can consist of a bunch of relational operators connected by logical connectives. You can see this is how it is done for the relational expression, which is consisting of relational operators. Now let us look at this complicated example: a smaller than b or c smaller than d and e smaller than f. We'll come back to that example many times. So we have first, okay, let us write the expression here. A smaller than b, a smaller than b or c smaller than d, and
Sir, if A is smaller than B, we will terminate it by 101.
yes, I'm coming to that, just a second. And e smaller than f. So this is the complicated expression. We like to evaluate it. So first we'll be doing a smaller than b. So what will be the corresponding semantic action? We can just get it from here. Assuming statements start from 100, Okay, we'll just write it here. So we'll have 100 if a smaller than b, go to 103. 101 is T1 is assigned the value 0. 102 go to 104, and in 103 you will have T1 is assigned the value 1, and now we have 104. Okay. So we have got E. E, this E is stored at T1. Now let us do for C smaller than D. So for C smaller than D, we have similar thing. Okay. So we can write here at 104, we can write similar things. We can just copy this guy. Instead of A smaller than B, we'll write C smaller than D. And instead of 103, we should write 104 plus 3, which is 107. And instead of T1, we should write T2. And here, instead of 104, we should write 10. So this is 104, this is 105, this is 106.
So actually, how we are terminating? A and B are terminal here.
I'll come to that. Okay, we are not yet done. We are just only evaluated two relational operators. So it will go to 108, and this is 107, and this is T2 is assigned the value 1. So we have evaluated A smaller than B and C smaller than D separately. We haven't really connected them together. Okay. Now we have E smaller than F. Okay. So starting from 108, we'll just have a copy of that. Okay. Let me draw the Parse tree. So this is E producing E smaller than F. Okay, so this tree will produce this kind of code. How? Yeah, so it will be E smaller than F, go to 108 plus 3, which is 111. At 109, we'll have the next temporary, which is T3, assign the value 0. At 1110, we'll have a go to statement, which will skip 111 and go to 112. At 111, we'll have T3 is assigned the value 1. So I am at 112. Okay. So now we have here we have this E placed at T2 and this E placed at T3. So you can see this logical expression, which is consisting of relational operators, are now consisting of E or E and E. So this is now nothing but E or E and E. So it has boiled down to this guy. Now it's easy. We have to create E producing E1 or E2 or E producing E1 and E2. These are the semantic actions. So what it is doing is it is assuming that AND has a higher precedence. So what it is doing is this E and this E, the AND operator is applied on them to produce this guy. So what is the corresponding action? You know very well that this E will create a new temp, say T4, and this T4 will be nothing but T2 and T3. So at 112, we can say T4 is assigned the value T2 and T3. Fine. What is the next step? The next step is this guy right here. This E or and this E, which is producing this E. So again, a new temporary is required, which is T5, which will be nothing but T1 or T4. So 113 will have T5 is assigned the value T1 or T4. That's it. Here you can see this is the overall translation scheme. It starts at 100 and ends at 113 because for each of the logical expressions consisting of relational operators, it has to emit 4 statements. 2 of them are goto and 2 of them are assignment of 0 or 1 to the temporaries, which will hold the value of the expression. All right. So this is the numerical way of translating relational expressions. As you will see, this is not the only way. We can do something else. Here the biggest problem is that you are creating temporaries and assigning 1 and 0. But is that how you want your true and false thing to be represented? That is the problem. May not be. Now, the next approach is known as flow of control Boolean expressions. So instead of numerical way, you can say, I can do flow of control. How? So here you need 2 more things known as E dot true and E dot false. Since you are not using numerical values, you are just using positional values. So where is your E dot true and where is your E dot false? That's it. You can just use some kind of a flow of control type thing for your logical expressions of the form a smaller than b. So instead of assigning zeros and ones explicitly to temporaries, what you can do is you can just transfer the control to E dot true and E dot false, which are nothing but labels. So you can say a smaller than b can be translated to if a smaller than b, go to E dot true, else go to E dot false. So these 2 statements are the only things which need to be produced if you are using flow of control way of translating of Boolean expressions or logical expressions. Okay. So you can see E producing ID1 relation of ID2. Here, what you need to do is, here they are using gen. You can easily use emit. Emit if ID1 place relational of ID2 place, go to E dot true and then go to E dot false. In that case, what is your E producing E1 or E2? That is the biggest question. So when you logically connect using logical connectives, the logical expressions, what happens? Now, if you look at E producing E1 or E2, if you look at E producing E1 or E2, now the question is, you have to assign E dot true and E dot false, because that's what we are doing now. Instead of E dot place, there is no E dot place needed because we are not depending on temporaries anymore, but we are depending on the branching labels, which is u1 dot, which depends on u1 dot true or e2 dot true, and u1 dot false or e2 dot false. Now, when we have e producing e1 or e2, let us take an example. Okay, so we have this thing a smaller than b or c smaller than d. So just like our previous thing, we have e and we have this thing, and what we have done is, instead of numerical, we have e smaller b go to say this, I say e1 dot true and go to e1 dot false, right? This is, say this is e1, this guy is e1, and similarly we might have e2, which is c smaller than d. So somewhere we'll be writing that part also. 103, if c smaller than d, go to e2 dot true, go to e2 dot false. Now comes this question. So we are creating e out of e1 or e2. Now what? What should e do? What should be e dot true and what should be e dot false? That is the question. Now let us get back here. Yes, any question? Okay.
স্যার একটা রিকোয়েস্ট ছিল।
Yes, বলো।
স্যার অ্যাকচুয়ালি আজকে আমার ইন্ডাস্ট্রিয়াল ট্রেনিং এর ভাইবা আছে, যদি 30 মিনিট আগে আমাকে একটু মানে ছেড়ে দেওয়ার পারমিশন দেন তাহলে
ঠিক আছে, ওকে, not a problem, not a problem. Okay. So now okay, now the question is, what is e dot u1 dot true, e2 dot true, and u1 dot false or e2 dot false? Okay. Okay. Now let us go back to here. Okay, we have this. So we don't know anything about u1 dot true or u1 dot false. Neither do we know anything about e2 dot true or e2 dot false. We just know that these are the variables we have. Okay. We don't have any labels explicitly set till now. So now when we evaluate a smaller than b or c smaller than d individually, we don't have any idea about their true or false branches. But when they get connected using some logical expressions like or, we have a clue. So now this e dot true and this e dot false is important. So you can say that if this guy is false, if a smaller than b is false, then what should you do? That means here this is turning out to be false. So that means it should do something. where should it go? It should look into this expression, whether it is true or false, because this is an OR connective. If the first expression is false for an OR, we need to evaluate the second expression, right? So why don't we generate a new label? Instead of a new temp, we generate a new label and we call it L1, and we say that U1.false can be this L1, which is the starting label for the second expression E2. So this is what is given here. As you can see, U1 or E2, here U1.false is given a new label. And then what about the truth value of E and U1? If U1 is true, if E is true, that implies U1 is true also. Okay. So only when you know that E is false. So basically, E and U1 are connected by a false, connected by, this E and E2 are connected by their truth values and false values. How? So if so, this whole thing is basically our E. This is our E1. This is our E2. So U1 has a true, E2 has a true, E has a true also, assuming they might not all be populated, as we'll see. In fact, most of the times they won't be populated in the first pass. They have to be populated. If we do a second pass, then only these U1 dot true, E2 dot true, U1 dot false, E2 dot false, these things will be available. Now, what I wanted to mean here is that U1 dot false should take me to a new level where we'll start the intermediate codes corresponding to E2. So that's why we can be sure about U1.false, which is nothing but a label where the next expression starts. So that is basically L1. We have no idea about U1.true, E2.true, and E2.false. But one thing we can be sure that if E is true, then both U1 and E2 are true. We cannot say the same thing about U1 and E2. We cannot say that if U1 is true, then E is true. We cannot say that. But we can be sure that if E is true, then U1 has to be true and E2 also has to be true. Okay? Similarly, we can say that if E is false, that implies E2 is false also. Okay, we have already seen U1.false, that is determined. But
sir, I can say from this that if U1 is true, so sir, I can conclude that if E is true and U1 should be necessarily true.
yes, absolutely. If E is true, then U1 is also necessarily true and E2 is also necessarily true. Correct. So we cannot say U1 dot true is assigned the value. Sorry, we cannot say E dot true is assigned the value U1 dot true. We cannot say this. This is not possible. This cannot be said. But we can definitely say this. This is definitely true. Okay? And similarly, we can say e2.f. So these statements u1.true is assigned the value e.true, e2.true is assigned the value e.true, and e2.false is assigned the value e.false. These are all necessarily true. Am I correct? So please note this. This is the important thing to understand. It might slightly appear counterintuitive because we always go from children to the uh, parent, but here you can see it's the other way around. So here, instead of synthesized attributes, we are actually using an inherited attribute. That's how it has happened. It has started. And you know, it is very difficult to find out during a bottom-up evaluation the inherited attributes. We have already seen that. Okay. Now, we said that one of the way to handle this is using the marker non-terminals. As we'll see, we have to use it. We'll see it a little later. Okay. So here we have the translation for a smaller than b or c smaller than d and e smaller than f. This is the way we have done the expression a little ago for the numerical way. Now you can see how it is done for flow of control way. You can see if a smaller than b, go to L true. L true is nothing but e dot true, which is the overall expression, some label, we don't know where it is. Then go to L1. L1 is the starting of E2. There, if C is smaller than D, go to E2 dot true. What is E2 dot true? E2 dot true means you have to evaluate E3, that is the last expression, E smaller than F. So you can generate the label because you know where the code for E smaller than F starts. Okay, but you don't know L false, or which is nothing but E2 dot false. Similarly, you don't have any idea about the last expression E smaller than F, what is the true or what is the false of it, but you know that this is going to be related to the true position of the overall expression, which is L true or L false. So that's how they have done the translation. So you can see the true and false exits for the entire expression is L true and L false. If you know them, then you can put those labels in appropriate places. As I said, the function new label returns a new symbolic label each time it is called. Each Boolean table has expression has two new attributes. E dot true is the label to which control flows if E is true. E dot false is the label to which control flows if E is false. There is another attribute S dot next. As I said, S is nothing but generally the assignment statements. So S dot next is the next statement following S. So these are the inherited attributes whose value is the label attached to the first instruction to be executed after the code of S. Okay. Now comes the, so we have till now done arithmetic and then we have done a little bit of logical expression. Now, these logical expressions in general appear with flow of control statements. So we have a flow of control way of translation of logical expressions. Now we are encountering the flow of control statements themselves in programming constructs. That's why these two are somehow very much interrelated. So
So what type of question can I expect from this flow of control part?
You can be given a small fragment and you have to translate into the ICG using the 3 address code.
So is there is any concept of leader in flow of control?
That will be coming a little later. We'll come to the leader concept a little later. Okay.
Yes, sir.
Okay. So what are the 3 types we are trying to handle here? One is if then, another is if then else, and another is while do. So here you know for if then, this is your format. If E, then S. The other one is if E, then S, else S. Of course, we will say S1 and S2 to distinguish them. And the third one we are going to do is while E, do S. That's it. So these are some of the example flow of control statements which can occur in programming languages. And as you can see, these statements necessarily have a logical expression as part of their construct. Has to be. Okay. So these two translations will be now merged. So we have already seen the flow of control and numerical way of translating of E. Now we'll see how the flow of control statements themselves get translated. So look at the architecture of if then, if you want to see the internal. So you have E dot code, which is the code for the expression, which we have to generate. Means A smaller than B or D smaller than E or something like that. So E can be a complicated expression. And then depending on that, which is basically the code of E, it will have a E dot true and it will have a E dot false exits. So if it is E dot true, it will go to basically the starting of S, which is the statement corresponding to if then S. So if E then S, so if E is true, then only it will go to S. And if it is E dot false, then it will go after the S. Now note that S need not be a single statement, it could be a block of statements, a sequence of statements. So E dot false need not be after the first statement of S, it will be after all of S. So please note that. That's why there is some separation between E dot true and E dot false on the upper left corner. The other one is if then else. So here E dot true will be basically S1 and E dot false will be basically S2. But once you go into E dot true, you execute S1 dot code, but then there should be a code go to statement which will skip the E dot false part. That is the most important part. I think you understand it. Okay, let me just do the slideshow and I'll show you here. So here what will happen is, here E dot true will make you come here and E dot false will make you come here. But then after S1 is finished, it should keep the if the else part and then it will come here. So this is what is S dot next. So the actual production rule here is S producing if E, then S1, else S2. So there is a S dot next. There is a S dot next. So this, after this, it will actually skip this S2 and come to this S dot next, which follows this whole statement. That is the point. So this is S dot next, not S2 dot next. Note that. It need not be following S2. It could be somewhere else. For while do, again we have E dot code and S1 dot code, which is easy. But here again there is a E dot true, which will basically come here and perform S1. After S1, you need to loop. So that means you need to go back to the beginning. This is the special thing. If E is false, it will go to S dot next, as here. All right. So these are the schemes of translation. Note these. So these are the flow of control statements. If E, then S1. If E, then S1 else S2, or while E, do S1. So in translating the if then statement, S producing if E then S1, a new label E dot true is created and attached to the first tiered S instruction generated for the statements S1, as I said just now. So E dot true will be the beginning of S1 right here. The code for E generates a jump to E dot true if E is true, and a jump to S dot next if E is false. Of course, it is true. So E dot false, this should go to S dot next, and E dot true should go to here, which is the starting of S1. So E dot false should be set to S dot next. So this is the rule for S producing if E then S1. As you can see, E dot false is set to S dot next. S1 dot next is also set to S dot next. And E dot true is basically a new label, which will be the starting of S1. As you can see, first E dot code would be there, then generate the E dot true label, followed by a colon, followed by S1 dot code right here. So this is basically your false exist. This is the S1 and S relationship. S1 dot text and S dot next are same. So S dot next is assigned to S1 dot next, because if we know S, then only we know S1, and then the corresponding code for the whole S is nothing but whatever code is generated for E and whatever code is generated for S1, as you can see right here and right here, and in between we have created the new label for E dot true. So that label followed by colon. So E dot code followed by a label with colon followed by S1 is going to be the whole of translation of if E then S1. Now this is very simple for if E then S1 else S2. Here in both true and false cases you need two labels. So you will have E dot true label followed by S1 dot code label, followed by S1 dot code, followed by a E dot false label, followed by S2 dot code. So this part is well understood. Then there is a E dot code which will be at the beginning, and S1 dot next and S2 dot next both point to S dot next, and there are two labels created for E dot true and E dot false. Now the important thing is after S1 dot code, you need to skip whole of E dot false and S2 dot code. So that's why the go to statement gen go to S dot next is created. For while, instead of next, we have a beginning also. In fact, we have next also. So you have a beginning right, sorry. We have a beginning right here. And E dot true, there is a label. E dot false, of course, this will be S dot next. It is similar to if E then S, only in a loop. S1 dot next, this one should not go out, but rather come back here. So that's why it is given as S dot begin. So your code would be S dot begin label, then E dot code, then E dot true, then S1 dot code, and this is the go to, which basically helps it to loop. So these are the semantic rules corresponding to this flow of statements. So let us try this guy now. While A smaller than B, so this is the thing we'll try now.
Sir, I'm leaving now, sir.
Okay, fine. No problem. I'll give you attendance, don't worry. This is the program we want to create the uh, intermediate code. Okay, so let us see how the parse tree looks like. So first it will be E producing C smaller than D. So this is E, and then we have the statement S producing if this, then the statement here is this guy. So let's call it S1 and let's call it S2. So S1 and else S2. Okay. So what is the rule for this? Let's keep the rule here as well. Okay. So if this is the rule, E dot true is new label. So let's try E dot true. So here E dot true is L1 and E dot false is L2. So two labels are created. Okay. Now S1 dot next is S dot next. So we don't know what is S dot next. S1 dot next is S dot next, but we don't know what is the value as yet. Okay. Then the next is S2 dot next is S1 dot next. Similarly, we don't know as of now. We'll see that sometimes we will not have the idea at all. Then we have the S dot code, which is E dot code. So S dot code is E dot code. So what is E dot code? Let us write the code here. We know how C minus D happens. So if C smaller than D, okay, if C is smaller than D, then go to E dot true and go to E dot false. Let's start this from say 100. Okay. Actually, it will be better if we start as it is. So what we are having here is essentially, let us write a little better one. While E to S. Okay. So this is how it is. I'll be better doing this way. while E to S. This is the starting S. Okay, this is basically the statement we are trying to parse. Okay, while E to S. We'll come to S little later. So what is E here? E here is A smaller than B. So while A smaller than B do, this whole thing is actually the S for while, and this is the E for while. Okay, so let us do the translation for while first. So what is the translation? The translation says S dot begin is new label. Okay, so we'll tag it here. S dot begin is new label. So let's call it L1. The next one is E dot true is new label. So E dot true is assigned the value L2. E dot false is S dot next. We don't know what it is. We have no idea what this is. S1 dot next is S dot begin. Okay. So S1 dot next, S1 is this guy right here. This is S1. So we'll use this. So S1 dot next is S dot begin, and S dot begin, assume it is 100. It starts from 100. S dot begin is, S dot begin is L1. Sorry, S dot begin is L1. Then we have S dot code, which is S dot begin. S dot begin means L1, and then we have E dot code. E dot code is this guy right here. So we'll have E dot code followed by E dot true. E dot true is L2. So there should be code for A smaller than B. I'll come to that just a second. Then once you have E dot code, you have the L2 label, which is E dot true, and then you have S1 dot code, whatever it is, and then finally you will have go to S dot begin, which is go to L1. Okay, so this is the first translation. Now we need to translate E dot code first. What is E dot code? We know that E dot code is this guy. If A smaller than B, then A smaller than B, go to E dot true and go to E dot false. This is what we know. Now, what is E dot true? E dot true is L2. So we can say it is go to L2, and we don't know what is E dot F. We have no idea because E dot F is assigned to S dot N, which is not yet populated. Okay. So instead of E dot code, we can copy this. So we can change E dot code to this guy. Okay. And then S1 dot code followed by go to L1. So this is how this much we have done. So this is, as you can see, L1, if A smaller than B, go to L2 and go to E dot false. We don't know what is go to E dot false. They have used L next. That is not a problem. We'll use it. And at the end, there is a go to L1, which is the S dot begin. Now we need to see what is S1 dot code. Okay. So what is S1? S1, as you can see, it is a if then else statement. If C smaller than D, then X is assigned the value Y plus Z, else X is assigned the value Y minus Z. So let us write that. S1 is a big if statement. So basically it is E. I am omitting if then else. So this is if E. Let's call it E2. Let's call it E1. If U1, then let's call it S2, else S3. Okay. So what is S2? S2 is nothing but X is assigned the value Y plus Z. Y plus Z. S3 is nothing but X producing Y minus Z. And this U1 is C smaller than D. Yeah. Okay. So that's better. So this is the one we are targeting. We are right here. We don't know what is S1 dot code. We don't know what is E dot F, but other things are known. So what is S1? S1 is nothing but the if then else statement as it is. So let's see the translation scheme here. Okay. What is the translation scheme? E dot true is new label, E dot false is new label. That means L3 and L4 will be created for E dot true and E dot false. This E corresponds to the expression for if then else. S1 dot next and S2 dot next. And let us populate these values. So here we are using U1 dot F. So U1 dot true is L3, U1 dot false is L4. Now S1 dot next, which is nothing but S2 dot next, is S1 dot n, and S1 dot n is actually defined, which is L1. Similarly, S3 dot next is S1 dot next, which is also defined as L1. So these things are known. Now we have to generate the code. S dot code is E dot code followed by a label E dot true, then S1 dot code followed by go to S dot next, then gen another label followed by S2 dot code. So let's see what is E dot code. Here it is basically E1 dot code. So we want to evaluate this guy. What is the code corresponds to this? What is this? If C smaller than D, go to U1 dot true or go to U1 dot false. Now what is U1 dot true? L3. L3 and go to U1 dot false is L4. Okay. So E dot code is available. So let us put it here. Right here, instead of this, we'll be copying this guy. Okay, so this much we have got, and the remaining part of s.code. So u1.code part is done. If c smaller than d, go to L3, go to L4. Yes, we are almost on the right track. Okay, then we have the label for u1.true. So we'll generate the label which is L3 colon followed by s1.code. What is s1.code? s1.code, as you can see, x is assigned the value y plus z. Okay. How does it get translated? As you can see here, t1 is assigned the value y plus z, x is assigned the value t1. So we'll do that. t1 is assigned the value y plus z, these are arithmetic expressions, and then x is assigned the value t1. We are done here. Then comes go to s.next. Go to s.next here is nothing but go to s1.next. s1.next is L1, so go to L1. So s1.next is L1. So go to L1. Yeah. So we are almost there. Then comes the code for e.false label. So e.false label is L4. We have already seen is u1.false in our case, which is L4. And here it would be basically the s2.code. In our case, it would be x is assigned the value y minus z. So t2 is assigned the value y minus z, and then x is assigned the value t2. And that's it. So that's it. Our translation is done. Here you can see we don't know s.next, which is a s for while statement. So that's why some labels are not yet done, like e.f is not done. Similarly, but we know s1.next, which is the s.begin, which is defined. We know u1.true and u1.false. We know s2.next and s3.next, which are nothing but s1.next, and that is L1. So some of these inherited attributes are filled in when we go ahead translating like this. But note that we did not get s.next, that's why we could not evaluate e.false. E is the expression for the while loop. So if you want to complete the translation, you might need more passes. Okay, single pass will not be sufficient. Okay, so now we go to the next one, which is a very powerful technique known as backpatching. So the easiest way to implement the syntax directed definition is to use two passes, construct a syntax tree for the input, and then work the tree in depth first order, computing the translations given in the definition. That's what exactly we did right now. The main problem with generating code for Boolean expressions and flow of control statements in a single pass is that during one single pass, we may not know the labels that control must go at the time the jump statements are generated. Like we have seen the s.next or e.false. This we couldn't properly evaluate. Now, one way of doing this, as I said in syntax related definition class, that one way you can handle this, that is basically you have to embed actions. And whenever you are embedding action, a bottom-up evaluator will not work. So if you have an inherited attribute and you are doing a bottom-up translation, you essentially need an embedded action inside the production rule, which is not defined during the bottom-up parse tree generation process. So you can put at the end of the production rule, which is not possible here. So what is the easy way out? As I said, you have to bring in a marker non-terminal. And this bringing in the marker non-terminal technique enables us with generating the label in a single pass, which is known as the backpatching technique. This is very important in our compiler, in our intermediate code generator. So we'll see, it is very easy actually. But before we go to backpatching, we generate quadruples and we have some more functions to manipulate these quadruples or the indexes to these quadruples. What is that? First is make list I. This is a function which will create a new list. Maybe I should do it in the other one. Yeah. So here, make list I, it creates a new list containing only I. So if you say make list 100, that means it will create a list of quadruples, but there the element will be only the statement corresponding to the address 101 or the quadruple address, quadruple level 101. You can make a larger list by concatenating them using the merge function. So merge P1, P2 will essentially merge two lists, P1 and P2, pointed to by P1 and P2, and it will return a pointer to the concatenated list. And then the third one is the function backpatch, which is the most important function. It inserts I as the target label for each of the statements on the list pointed to by P. So in P, if you have 3 go-to statements, then each of these go-to statements will have I as the label. So using backpatch, you can easily populate all those undefined fields, as we'll see shortly. Now, how do we do the Boolean expressions now? We insert a marker non-terminal M into the grammar to cause a semantic action to pick up at appropriate times the index of the next quadruple to be generated. That is the key thing. Sometimes we could not generate it because we didn't know where to generate where the control is going to flow. Like here, like in our example, here we don't know, we have no idea what is s dot next. We don't know. That's why we had to leave these unspecified, this guy, e dot f. But if we somehow could track where it is actually leading us to, in fact, these marker non-terminals will help us do that. Synthesized attributes true list and false list of non-terminal E are used to generate jumping code for Boolean expressions. So since true list and false list will be available, now instead of inherited attributes, now you use a synthesized attribute, true and false list. So whenever the parse tree is created, these values are available. But as you know, this dot next is an inherited attribute. So how do we populate the inherited attribute? Using the marker non-terminal and backpatching. As code is generated for E, jumps to the true and false exits are left incomplete, but these incomplete jumps are placed on list pointed to by E dot true list and E dot false list. Then the backpatching will take care of this population. So here you can see like E producing E1 or E2, we dealt with that. But now, in order to keep track of where E2 is starting or where the E dot false list or E dot true list will go, we keep this guy. This is the marker non-terminal. As you can see, the only activity of the marker non-terminal is to create an epsilon, but in the process, it will populate the attribute called quad, which is what is the next quadruple it is trying to point to. That means it will exactly point to where E2 is going to start. That's what it is. Similarly, for E1 and E2, you can see there is a name. That's it. No other place you need this. So now the question is, what is the task? So immediately you say that for E1 or E2, this is the rule, E1 or ME2. So if E1 is false, that means the list pointed to by E1, all those things will be pointing to this guy, like where M is. And M is nothing but M dot quad. So you can see M producing epsilon. What it is doing is, it is populating the attribute M dot quad as the next quad. Next quad means wherever it is available. M will tell its own place. That means the current statement number, quadruple number, it will point to. Now, what is E dot true list and what is E dot false list? So E dot false list is whatever is the false list pointed to by E2, that will be the false list pointed to by E as well. E dot true list is basically whatever is concatenation of E dot E1 true list and E dot true list, because E will be true only when both E1 and E2 are true. Now you know both E1 dot true list and E2 dot true list because these are synthesized attributes. So now you can generate E dot true list. And E dot false list is nothing but the false list pointed to by E2. Now, the other thing to look for is rule number 5, which is ID1 relation of ID2. So what you do here is you definitely generate these statements as you have already done. If ID1 dot place relation of ID2 dot place, go to this and then go to this. These are the true and false statements corresponding to this relational operator based logical expression. But then you create the additional two things, which is the true list and false list as well. So true list is this guy, false list is this guy. That's what it is. Next quad is this guy, next plus one is this guy. So if statement is next quad, just the plain go to statements is next quad plus one. So right here, you start making the list. And these are the true list and false list, which are synthesized by these expressions to create more and more longer list. An example will definitely clarify the whole thing. Let me see if I have enough time or not. It is already 2:07. So I'll start from this particular PPT page on Friday. So as I said, on Friday, we have a class starting from 10:50 a.m. It will continue till 11:40, 11:45 a.m. So on that day, we'll complete this ICG. Basically, the backpatching technique is pending. And we'll see how backpatching helps us for if then else as well as while do. And that would be the end of ICG. So as I said, please be present on this Friday. I'll be taking your attendance just now, so don't go away as yet. Let me take your attendance. There is no class tomorrow, so we'll meet Friday 14th at 10:50.